Well, hello, good people. Today we are talking about rainbows and bubbles. Now, before we start talking about rainbows and bubbles, we have to talk about how light could get separated into all of its individual colors. So we'll start by talking about prisms. Oh gosh, no spoilers, no spoilers. Okay, here we go. Perfect. Here I have an image of a prism dividing light into its individual frequencies. Now, when Isaac Newton first held a prism up to some white light, and he saw the prism doing this, spreading light out into all of its frequencies, he kind of freaked out a little bit. And there was good reason. People at the time believed that white light was the purest form of light, that you couldn't break down white light into any of the other colors of light. But this showed that white light was actually made up of various frequencies of light, something that we all now know to be true, that white light is composed of all of the frequencies on the visible spectrum. But at the time, this was completely shocking, and it revolutionized the way that we understand light. Now, today we know that visible light, white light, is made up of all the different frequencies, but what we're going to understand now, and the question that I want to ask you is, how does a prism actually take white light and divide it into these frequencies? Well, let's see if we can understand it by drawing a picture. Here, I am going to draw a prism. Oh, quite lovely, yes. Now, imagine that white light were to go into this prism. We know that when light changes mediums, like if it were to go from air here to this glass here, when light changes mediums, it refracts, it bends because it slows down. We know that all light in a vacuum travels at the same speed. All light in a vacuum travels at the speed c, 299792458 meters per second. But when light gets into a new medium, when it changes, not all light travels the same speed. It turns out that some frequencies of light travel faster and other frequencies of light travel slower in new mediums. And there's a reason for that. If you had a really long wavelength like this, and that long wavelength light traveled through your prism, well, it wouldn't spend much time interacting with the molecules because the wavelength is so long that it could just kind of coast on through. But if you had a really small wavelength, like really small wavelength light on its way in, that small wavelength light would really significantly interact with each little molecule because it would hit a little molecule, it would excite that little electron, the electron would jump up, and then it would jump back down, and when it jumps back down, it releases a little photon. The little photon zips on until it hits the next molecule, then it gets absorbed by that little electron, then that electron drops down, gives off another little photon, and that photon goes on from molecule to molecule to molecule to molecule. So we see that smaller wavelengths of light actually interact way more with the medium that they're in than these longer wavelengths. These longer wavelengths of light just kind of can coast on through, but the smaller wavelengths spend more time interacting with the molecules. This is true on a big range. Like radio waves have a much easier time getting through mediums than things like X-rays or gamma rays. They'll spend a lot more time hanging out in each individual molecule, but it's also true on the visible light spectrum. It turns out that when red light hits a new medium, that red light coasts through a little bit easier than something that has a higher frequency or shorter wavelength. Something like violet light, which has a very short wavelength, has a harder time getting through because it spends so much time interacting with each little molecule. Now, this means that when you send in white light, which is composed of all of the frequencies of light, all of the colors, different frequencies within that white light are going to interact with the new medium differently. For example, if you send in some red light, oh wow, let me try again. My apologies, dear people. If you send in some red light like this, when that red light gets to that prism, it's going to slow down, but it's not going to slow down a ton because it's not going to spend much time interacting with each little molecule. So it's going to slow down a little bit, which means it's going to bend a little bit. But if you send in something like violet light, well, violet light has a nice high frequency, a nice short wavelength. So when that violet light comes in, when that violet light gets to the prism, it's going to slow down a lot. And so it's going to bend a lot. And it's going to bend really significantly. Actually, I'm going to draw it bending even more significantly. Like this significant. Okay, well, that is a little bit excessive. Okay, but you get the idea. Bends very significantly. And all of the other colors at each of their other wavelengths kind of fill in the gaps in between. The blue light will also slow down, not quite as much as the violet light, but still pretty substantially, and so it'll bend quite a bit. The green light will slow down somewhere in the middle. Oh gosh, we're still on blue. Well, that was embarrassing. Oh my. The green light will slow down quite a bit as well, but not as much as the blue. Orange light or yellow light will slow down much less because its wavelengths are much longer. And finally, red light will slow down the least, and so it'll bend the least. This effectively breaks white light down into all of its constituent frequencies. When the white light comes in, the violet light bends the most, the red light bends the least, and all the other frequencies are somewhere in between. This process of bending light into its constituent frequencies is called dispersion. Dispersion occurs when light is bent into its constituent frequencies due to the varying indices of refraction of different wavelengths of light. In other words, longer wavelengths bend less, shorter wavelengths bend more, and so all the frequencies of light spread out. Now you can see all the colors of a rainbow here, but this is not a rainbow. To have a rainbow, you need rain. And so, when you have a rainbow happening, what's occurring in the sky is that each little raindrop is acting like its own little prism. So you have white light that enters the raindrop from the sun. When that white light enters, it has some red light in it. And when that red light goes into the raindrop, it bends a little bit, less than that. It bends a little bit, but not a lot of it. Oh gosh, I am so sorry. My perfectionist tendencies are grabbing a hold of me. Okay, here we go. Okay, it bends a little bit. When the violet light enters the raindrop, since that white light is made up of all the different frequencies of light, when the violet light enters that raindrop, it bends pretty substantially here. And so you could see how a raindrop could act just like a little prism, and it would break all of the colors of light into all of its frequencies, dispersing the light just like a prism does. And you could imagine that the orange light would be here, then yellow, then green, then blue, then indigo, then violet. You'd get all the colors of a rainbow. But that's not where a rainbow happens. That's not where the story ends. Because when these little light rays get to the back of the raindrop, they don't just stop here. They actually keep going. Part of this light wave is going to keep on going through back into the air behind the raindrop. But part of it is going to be reflected off the back of the raindrop like this. And then when it gets to the new medium out here, it's going to get refracted once again, kind of like this. Oh gosh, that is a terrible refraction. Yeah, you get the general idea. Pretend that is an even worse refraction. This is just embarrassing, but pretend that it bends, okay? The red light, likewise, is going to bounce off the back of this raindrop, and then when it gets to the layer between the raindrop and the air, it is also going to refract once again. So this raindrop is doing a lot of things. First, it refracts the light, dispersing it into its colors. Then the light reflects off the back of the raindrop. And then, once again, it refracts on the way out of the raindrop. So you get a little refraction sandwich here with refraction, reflection, and refraction at the end. This is what creates the rainbows that we see in the sky. What happens is the sun has to be located in the sky nice and low in the horizon, like right here. Here's my little sun, low in the horizon. It sends light into the raindrop. Then that light refracts, reflects, and refracts back out again. Then you are standing down on the ground and you see the light from that little raindrop entering into your eye. And that's how you see a rainbow. Now, a few things that have to be true here. First, the sun has to be back behind you and it has to be really low in the sky. It turns out that with all of this refraction and reflection and refraction that's happening again, the angle between the incoming light and the final refracted light that's coming out of the front of the raindrop again, that angle, theta, we'll call it, is always equal to 42 degrees. So here's what has to be true. The sun has to be relatively low in the sky. If it's not low enough in the sky, then the light will come into the raindrop, bounce off, but it'll bounce off above your head so that you'll actually never get to see the light. The only way that you get to see it is if the sun is low enough in the sky that 42-degree angle is actually going to come into contact with your eye. So the sun has to be low in the sky. That's why we normally see rainbows in the evening or early in the mornings, not in the middle of the day. And then secondly, it has to be true that the raindrop is out in front of you, because if the raindrop is back behind you, then you won't actually be able to see the reflected light rays that are coming off the back of the raindrop. So these are some of the things that are important, that are essential for rainbows to happen. Now, here's the truth, is that a rainbow can't just happen with one raindrop. In order to make a rainbow, you're going to need a lot of raindrops, and I'll show you why. Okay. Now, here, what I have in this image is actually, it's an image that I took from a video that is called, here, I can write it out for you here, or maybe this will take way too much time and I'll give up. I'm feeling that it's going to be the second. It's a video called Newton's Apple. And this video is called Why Are Rainbows Curved? Or Why Rainbows Are Curved, something along those lines. Newton's Apple was a show that aired on PBS in like the late 80s, early 90s. In this video, you can tell it's totally late 80s, early 90s. It's just beautiful, all the 80s, 90s kind of vibes. But this video on this TV show, they literally would just send in physics questions or send in science questions, and then they just answer them on the show. Can you not think of a better show? Like, I just want to watch that show all day long. That just sounds wonderful. But this particular episode is answering a question, answering a question sent in from a viewer, and the question is why rainbows are curved, or why are rainbows curved? I highly recommend watching this video because it is just absolutely delightful and it explains a bunch of physics. But the main thing that I want you to get from this video, I'm going to show you here together from this little image from the video. So here's the idea. In order to see a rainbow, you're going to need a lot of raindrops. And actually, this is kind of in my way here, so I'm going to move it. Maybe I won't move it. I'm going to attempt to move it up here. Thank you for your patience. You are so very kind in your patience. Okay, so here's the idea. The idea is if you're going to see a rainbow, then your eye has to be located in the place where all of the light is coming to. If your eye is not receiving the light, then you don't see it. So, in order for you to see a rainbow, you have to be in the perfect position where all of the light is coming into your eye. Now, here's what's true, is that each rainbow, or each little raindrop, is creating its whole own little rainbow, but you're not going to see all of the colors, because all of the colors aren't going to make it to your eye. Only one of the colors is going to make it to your eye. Let me explain. Do you see how first here, this thing is going to make a nice 42-degree angle every single time? Well, depending on the position of that raindrop has to be perfectly positioned so that the light comes into you at that angle of 42 degrees. So the drop has to be 42 degrees above you. When the light from that drop gets to you, not all of it is going to be perfectly positioned to hit your eye. Check it out. For this one, the violet light is going way too high. This violet light would hit you straight in the forehead. It wouldn't make it into your eye. This blue light would hit you in the eyebrow when it hit you in the eye. But the green light is perfectly positioned to hit you in the eye. The yellow light will hit you in the chin. The red light will hit you on your collarbone. And so the only light that you're going to see from this particular raindrop right here, the only light that you would be able to see from this raindrop would be the green light. And that is a terrible... Anyway, okay, well, I guess we're just going to leave it. The only light that you would see from this raindrop would be the green light. If you wanted to see red light, you would need a raindrop that's located a little bit higher, like this one. This raindrop is sending red light that'll hit you square in the eye, but the orange light will hit your eyebrow, the green light will hit your forehead, and the violet light and the blue light will pass straight over your head and you won't be able to see them. If you wanted to see one of the lower colors, you would need something like violet, you would need a raindrop lower down in the sky, something like right here. This raindrop lower down in the sky would send purple to your eye, that violet color, but the blue light and the green light and the yellow light and the orange light and the red light would all be way too low. They would all hit you in the face below your eyes, and so you wouldn't be able to see those colors. So in order to see all of the colors of the rainbow, you need a whole array of raindrops. And you can imagine if you wanted to see the color orange, you would need a raindrop here in between the raindrop that's sending you red and the raindrop that's sending you green. And if you wanted to see the color blue, well, you need a raindrop here in between the raindrop that's sending you green and the raindrop that's sending you violet. So the only way that this is going to work where you're actually going to see a rainbow is if you have a whole sheet of raindrops that are each sending you individual colors. Everything has to be perfectly positioned so that all of the light is coming to your eye. This is why one raindrop is not enough to make the full rainbow. You need a ton of raindrops, a lot of water that's all doing this whole dispersion thing, that's all doing the reflection thing, that's all doing the refraction thing to get it all to your eye. Now, this means that every single person is going to need to see their own set of raindrops. If I'm standing right here, there is one particular set of raindrops that are going to make it to my eye. But if my buddy is standing over here, there's a totally different set of raindrops that will be perfectly positioned to make it into his eye. And if my other friend is standing over here, well, there's another perfect set of raindrops that are going to make it into her eye. But we're not all going to need the same set of raindrops. We each need a different set of raindrops that are perfectly positioned perfectly for us, which is why every single person gets their own rainbow. We all look at the same sky, but my set of raindrops is different than my neighbor's set of raindrops because each of our raindrops has to be perfectly placed so that the light makes it into our eye. Isn't that just wonderful? That's a little bit about why you need a whole set of raindrops in order to see a rainbow. Because if you don't have a whole set of raindrops, then you'll only see one of the colors. Now, here's something else that's true. Is that if you look up at the sky and you see a rainbow, you'll see that that rainbow is always at a nice curve. And again, they have a beautiful demonstration of this in the Newton's Apple video, why rainbows are curved. I show a portion of it in class. It's very, very nice. It's a 6-minute video. Like seriously, if I could recommend a video that's not a Miss Wilson's Physics YouTube channel video, I would highly recommend this video because it's just wonderful. But anyway, so they have this whole portion where they talk about why is the rainbow actually curved? Well, the reason why it's actually curved is because you have to maintain this 42-degree angle between yourself and the incoming light. And in order to maintain that 42-degree angle, you know how like if you have your compass, wait, I'm going to make this big really quick. You know how like if you have your compass like this, and this is like, this will be like the not moving part of the compass, and this is the part of the compass that moves. If you keep it at a 42-degree angle and you want it to stay at a 42-degree angle, well then when you rotate it, it creates a nice little curve. A rainbow does the same thing because all of the light has to come to your eyes at a 42-degree angle. No other angle will work. And so that's a little bit about why rainbows have to be curved. Now there's one other question that they answer in the video, and that last question is, where does a double rainbow come from? So we're going to talk about where a double rainbow comes from. Okay, hello. Let's look at a little double rainbow situation here. Here you can see a beautiful picture of a double rainbow. I got the primary rainbow on the bottom and this secondary rainbow up here. A few things to notice about the secondary rainbow. Notice that the secondary rainbow is much fainter up in the sky, and also notice that the colors are inverted. Check it out. This bottom rainbow goes red, orange, yellow, green, blue, indigo, violet. The top rainbow goes violet, indigo, blue, green, yellow, orange, red. It goes in the opposite order. There's a reason for that. Check it out. Here, let's draw a little raindrop. You could imagine that the light comes into that raindrop. When the light gets into that raindrop, it's going to refract, then it's going to reflect, and then it's going to refract back out again, kind of something like this. Well, imagine that part of this light, once it's going to reflect and then it'll refract, or it'll reflect here and then it will refract out. But some of this light is not going to get transmitted when it meets the edge of the raindrop here. Could you imagine that some of that light would actually get reflected again off the edge? And then that light would then finally get refracted out? Here's the truth is that any time you have rain like this, you have rain falling in the sky, the light ray will come in, it'll reflect off the back, then refract out, but some of it at this second refraction point actually won't reflect. or actually won't transmit out. Some of it will actually reflect again and end up out here before it refracts out once more. This means that when you're looking up at the sky, there are two light rays coming to you from every raindrop. One is from the first bounce and the other one is from the second bounce. The light from the second bounce creates a secondary rainbow. That secondary rainbow is up higher in the sky, just like this comes out higher here. And instead of coming in at a 42-degree angle, it's going to come in at a 51-degree angle. Notice that this is much fainter than the primary rainbow. The reason for that is because most of the light is actually going to make it out of the raindrop. It's less of the light that does the double bounce and then comes out again. So most of the light just makes it out the first time. It's only a little bit of light that does that second bounce. And the third thing to notice here, I say third, I don't even know if we had a first or a second, but there we go. I felt like third was right. Okay, so the third thing here is that you'll see that all the colors are flipped. That's because when this bounce happens here, when you get that little bounce, it's going to flip all the colors. So instead of coming out with violet on the top and red on the bottom so that the highest up raindrop gives you red and the lowest down raindrop gives you violet, it's going to be flip-flop. You're going to have red come out on the top, violet coming down on the bottom, so you're going to need the highest raindrop to show you red and the highest raindrop to show you violet and the lowest raindrop to show you red. So the colors get flipped there. And that's a little bit about double rainbows. Now you know a lot of things about rainbows. You understand how each little raindrop acts like a little prism. You understand how you need a whole sheet of rain in order to be able to see a rainbow, since each raindrop is only going to send you an individual light ray. You understand how those light rays are always coming in at an angle of 42 degrees, which means that you have to have a nice curve here in order to maintain that 42-degree angle. And lastly, you understand how double rainbows are caused by a double bounce inside the raindrop. The next thing that we're going to talk about today is bubbles, and how bubbles can have a really interesting effect due to what we call thin film interference. Here we go. Now here's a question for you, is what color is a bubble? Well, you look at a bubble and you'd say it's clear, but if you look closely, you see that the answer is actually much more complex than that. Do you see that in the surface of this bubble, you can see tons of different colors? You can see magenta, you can see cyan, you can see yellow. Interesting. How does that happen? You might be wondering. Well, I have great news for you, good wanderer. And the great news is that the answer is within the bounds of your ability to comprehend. And so we are going to learn now why bubbles have so many colors on their surfaces. Why is a bubble rainbow colored? Let's take a look at a picture. Oh gosh, oh that's embarrassing. Don't look, spoilers. They're all there. Hide your eyes, shield them. Okay, you're safe now. Okay. Let's talk about bubbles. Why can you see all of the colors on the surface of a soap bubble? Well, first, you need to know that the correct answer you could give in 3 words, and those 3 words would be thin film interference. And so now you say, cool, Miss Wilson, I think I understand it. I think I'm ready to go. I got thin film interference, except that, what exactly is thin film interference? Well, I am so very glad you asked. In order to understand thin film interference, you have to understand what a bubble looks like and how a bubble works. So let's draw a little picture of a bubble. Actually, I'm going to draw a little bubble right here. Here is a little bubble. Okay, that's fine. Yeah, sure, we'll use that. Okay, whatever. It's whatever. It's really fine. Okay, this is a soap bubble. On the inside of this soap bubble is air, and on the outside of this soap bubble is also air, but in between is where things get really interesting. Here you have a little bit of soap on the outside, and here you have more soap on the inside. So you have 2 layers of soap. And squished between those 2 layers of soap right here is water. You got water squished between 2 layers of soap. Now, if you know anything about soap, you know that soap has 2 parts to it. It has a part that's hydrophilic and a part that's hydrophobic. And so the parts that are hydrophobic hang out on the outside here, little hydrophobic parts, and also right here, and the little hydrophilic parts, kind of like if you have like a membrane to a cell, a very, very similar concept for a soap bubble. those little hydrophilic parts, they surround the water, and so then you get water and then soap on each side. And this creates a little bubble of air. Now, here's the question is, how do we see all of the colors? Well, the place where we see all of the colors is in this thin film of soap around the air. So let's take a little zoom in picture and let's look at a part of this film and see what we can find. I'm going to zoom in right here on this little part of the bubble, and I'm going to draw it sideways like this. So if you could look at this little part of the bubble, if you could zoom in on this layer, you would see something that looks like this. Actually, I'm going to draw it a little bit there. Something that looks like this. This is your soap bubble right here. Here you have soap, here you have your water, here you have your soap. And let's say that the thickness of this film of the soap bubble is a thickness T for right now. Now here's what's going to happen is that light is going to come in towards this bubble. All the different frequencies of light are going to come in towards this bubble, and they're going to hit the surface of the bubble, and some things are going to happen. Let's see if we can take a look. If you have light coming in towards the surface of this bubble, the light is going to hit this bubble, and when it gets to this bubble, it's going to, well, I should say two things are going to happen to it. The light comes in, and part of the light is going to make it through the first layer like this. And when it makes it through the first layer, it's going to refract slightly. But part of the soap, or part of the light is not going to refract. Part of it is going to reflect off of the surface of the bubble like this. So we have one light wave that comes in and it splits into two parts. Part of it reflects and part of it transmits and refracts. Now, once this second part, the part that transmitted and refracted, once this part gets to the second layer here, then now new things are going to happen to it. When it gets to the second layer, it's actually going to have two things happen once again. Part of it is going to refract as it enters into the air that's on the other side, this air that's trapped on the inside here, and part of it is going to reflect back this way. And when it reflects back, now part of it once again is going to reflect off, and part of it is going to refract through to the other side. And here my arrows are not really all that great. They really should look something more like this. My angles just aren't superb, but the idea is generally good. Okay. So here's what happens. There are two light rays that you need to pay attention to. One light ray bounces off the first surface. The other light ray makes it through, hits the second surface, and then bounces off of the second surface. Now, these two light rays, these two reflected light rays, are going to interact with each other. And that interaction of these two reflected light rays with each other is what's going to cause all of the colors that you see on the surface of a bubble. Let's see how they could possibly interact to cause all of those different colors. Well, let's say, for this example, that the thickness of the bubble at this particular spot on my bubble is equal to 1/2 of the wavelength of blue light, which is totally possible. It's a very, very small thickness, but as you know, bubbles are very, very thin. So you could have a place where the thickness of the bubble is equal to half the wavelength of blue light. Well, then here's what would happen, and I'm going to draw like a ton of things on this diagram, so it might get a little bit dicey here. So I'm probably going to switch to chalk. Wow, is this going to work? I've never tried chalk before. Let's switch to chalk and see how it does. Okay, so you're going to have a light ray that is coming in like this. When it hits this outer wall, the light ray that hits the outer wall is going to reflect off, and it's going to reflect off inverted. This little outer wall is going to act like a fixed end. And so this thing came in as a crest and then a trough. It's not going to come back as a trough. It's going to come back as a crest and then a trough. When it reflects off, I'm going to draw that one more time, as a crest and then a trough like this. And now I'm going to make this reflected light ray just a little bit darker here by adding just a wee bit of, oh, wow, no need to be excessive, okay? By adding just a little bit of pen here so that maybe we add, sorry, I just really want you to be able to see all these different lines because all of the different lines are actually going to be really important. Maybe we add some pencil here, and maybe we make that pencil, I want to stay in the blue vein. Gosh, I'm just debating too much here. Let's go to this one. Okay, You guys are like, just get on with it, Miss Wilson. Okay, I am really very much trying. Okay, here we go. So here's your reflected light ray like this. So your light ray comes in. When it comes in, part of it reflects, and that part that reflects off the first layer, off the first wall of the soap bubble, is going to reflect back inverted. So it's going to come back upside down. But part of it is going to get transmitted. Let's go back to our chalk. Chalk. Part of it is going to get transmitted. And when it gets transmitted, here's my incoming light ray. It goes like this. It's going to get transmitted like this. And it's going to make it through. Now this part is now going to hit the next end of the bubble. When it hits this inner layer of the bubble, it's going to come back like it just got reflected off of a free end. So it's going to come back off that reflection uninverted. Came in as a crest in this example, so it's going to come back as a little crest. And then it'll ride that little wave right out of there. Wait, I want to draw this a little bit better. So sorry. It's just that all these things are really going to matter. Okay. So here's what you see. Here's your second reflected light ray is right here. This one is the one that reflects off the inner layer of the bubble. So now we have two reflected light rays, one that reflected off the outer surface and one that reflected off the inner surface. And they look like this when they come out, and these two are going to interact with each other. I'm going to draw them off to the side slightly so that you can see them. Here's your first reflected light ray. This one came off of the first layer. Your second reflected light ray came off of the second layer, and it looks more like this. Oh gosh, oh gosh. Okay, take two. Wow, thank you for your patience. I do so appreciate it. Okay, here's your second light ray. Notice the second light ray, the one that reflected off the inside layer, is longer than the first light ray because it had to take a longer path to get out because it had a longer trip to go. It had to go through the thickness of the whole bubble. Because the thickness of the bubble is half a wavelength, that means that these two waves are perfectly half a wavelength off from each other. Check it out. That means that once they get outside of the bubble, this wavelength like this and this wavelength like this, these two reflected light rays, one from the inside and one from the outside, these two reflected light rays will cancel out with each other through destructive interference. Because they experience destructive interference, that means at this point on the bubble, you won't be able to see the color blue because all of the blue light rays will destructively interfere with each other. However, you will be able to see colors like red and green because when red and green come in, those red and those green rays will just kind of coast on in like this. They'll kind of coast back on out like this, and they will not destructively interfere with each other. They'll constructively interfere. So you'll still be able to see green light rays and red light rays from this point. And since you can still see the green and the red, you'll be able to see at this point on the bubble yellow, but you won't see blue. That means this little spot on the bubble will end up yellow. Let's take a look at another little spot on the bubble. Right here. You can see this part of the bubble is much thicker. Let's take a look at what it would look like. And now I'm going to do some serious eraser work, and so I am going to, why does it not like when I try to go to eraser mode? It's like, no, you want to erase? Absolutely not. And I'm like, yes, I would like to erase actually. So if you could let that happen, that would be just so spectacular. I'm going to make this like a supersized, like your McDonald's burger kind of eraser. Okay. Here we go. Supersized. Yes, yes, yes. Bye. Thank you all for showing up. It was so lovely to have you here. Goodbye, blue. Hello to our next little experience here, which is the thicker part of the bubble. Okay, here we go, here we go, here we go. Back to our pen. Let's look at the thicker part of the bubble. Let's say that at the thicker part of the bubble, the thickness was equal to not half the wavelength of blue light. Well, what if here the thickness of this little section is equal to T equals half the wavelength of red light. That means that the same thing is going to happen here. Red light is going to be on its way in. When the red light gets here, part of it's going to reflect. The part that reflects is going to get inverted, so it'll come back like this. but part of this wavelength is going to make its way through. When it makes its way through, it's going to get to here, and it's going to reflect back upright like so. And so then you're going to get two reflected light rays, one off the outside of the bubble, one off the inside of the bubble. These two light rays, here's one right here. That one's reflected off the outside of the bubble, this one right here. Then you have this one right here, which got reflected off the inside part of the bubble, right here. Those two light rays, when they interact with each other, they'll destructively interfere because you'll have crests lined up with troughs and crests lined up with troughs. So they'll destructively interfere and you won't see the color red here. What you will see is colors like blue, and you'll also see colors like green, which means right at this section of the bubble, you'll see the color cyan. You could imagine how there could be another spot that's kind of a medium thickness where you wouldn't see the color green because of its thickness. And so at those spots where your bubble is like a medium-ish kind of thickness, spots like this one, the bubble would appear cyan colored because, magenta colored because, wait, did I mix up all my colors here? Did I say that this one would appear cyan colored because you see green and blue? I hope that's what I said. Then right here, you would see that this spot right here would appear magenta colored because you would not be able to see green, but you would be able to see the other colors. You'd be able to see the blue and the red. This creates a bubble that has different colors all over the surface. And also, if you look at a bubble, you'll see that the colors on a bubble are kind of swirling all the time. That's because the thickness of a bubble is constantly changing as it moves through the air, and as that film is getting pulled down by gravity, you have all those colors keep constantly shifting as the film thickness changes. This is what we call thin film interference, and it's a result of two reflected light rays, one off the first part of very thin film and one off the second part of very thin film. Those two add together to create either constructive or destructive interference to create the colors that you see. You see this in bubbles, but you also see this if you ever see some oil spilled on the pavement and you look down at that oil, you'll see that you can see almost all the colors of the rainbow in that oil. It kind of looks like the surface of a bubble. That's because you have a very thin layer of oil that varies in thickness all along. And so since you have that thin layer of oil, you have the same thing going on here where you have light rays coming in, bouncing off the first layer, light rays coming in, bouncing off the second layer. Those two reflected light rays interact with each other in one way or another, either in phase to create constructive interference or out of phase to create destructive interference. And so then you can see all the colors of light in the little oil. And that, ladies and gents, is just about all for rainbows and bubbles. You learned a lot about rainbows and how they work. You also learned about how bubbles create all of the colors of the rainbow due to thin film interference, where you have interaction between these light rays that are reflecting off of both layers of the film. And that is all for today, folks. I hope you have a wonderful rest of your day, and I'll see you here next time, virtually. Bye, good people.